Here we've got a problem involving two masses. A smaller 50 kilogram mass is pushing against a 100 kilogram mass, and a force is applied to the right, acting directly on the 50 kilogram mass that drives the whole system. Now there's also some friction in this case, so I've started the free body diagram. So I've labeled the applied force of 450 newtons. Each mass has a force of gravity straight down, which I labeled Fg1 and Fg2, so we can distinguish between the two. F normal 1 and F normal 2 are equal and opposite to those two respective forces of gravity. They are equal and opposite because there is no net force vertically, so the forces must balance in that direction. So all those blue forces cancel each other off. Now we're missing some horizontal forces. We have some friction. We know that the coefficient is 0.2. So as this box is being accelerated to the right, friction is slowing it down to the left. So there'll be a force of friction acting on block 1, which I'll call force of friction 1, as well as a force of friction acting on block 2, which I'll call force of friction 2. Now block 1 pushes on block 2 with some sort of contact force, and because of Newton's third law, block 2 will push back on block 1 with an equal and opposite force. Forces always come in pairs when you're talking about systems and interactions between objects. So those two FCs are equal and opposite. Now notice that all these forces that are labeled in green are the forces that are driving the system to the right. All the blue ones cancel each other off. So if I look at the entire system, in other words, considered as one big mass, and I do my second law, F net is just the sum of the forces, but we have to watch the direction, the vector nature of those forces. Then I get an equation that looks like this. F net is always ma, and it doesn't matter how we sum up the forces, we can do them in any order we like, but I've got 450 to the right, and then I've got friction to the left, force of friction 1. Same with force of friction 2, both those are subtracted. They're both opposing the motion. And then I've got this first FC, which acts on mass 1, which is to the left, and anything to the left we've defined as negative. And then we've also got an FC, which acts on the 100 kilogram mass, that's equal and opposite to the right. So there's my driving system equation for both masses combined. And because we used forces from all the masses, this net force must be the total mass. So notice my FCs, because they're equal and opposite, cancel each other off, and I get an equation that will allow us to solve for the acceleration. So my total mass is 50 plus 100. We're looking for A. That first force was 450, we knew that, and we know the formula for force of friction. Mu times the normal. So force of friction 1 will be mu times Fn1. Force of friction 2, mu times Fn2. Now those two Fn's, recall, are equal and opposite to the respective forces of gravity. So Fn1 is just m1 times g. Fn2 is just m2 times g. So when we do all our substitutions and solve it for A, we end up with an equation that looks like this. My acceleration will be 450 minus mu, now mu is given as 0.2, times mass 1 times 9.8 minus mu times mass 2 times 9.8. And this entire thing, because I'm trying to get my acceleration by itself, I'm dividing the entire thing by 50 plus 100. So the entire right-hand side gets divided by 150, which is 50 plus 100. And you end up getting an acceleration for the system. I'm going to put it over here to the left, to be 1.04. So the whole system is accelerating to the right with an acceleration of 1.04 meters per second squared. Now, we want to figure out these contact forces. That was the second part of this question. Notice they cancel off when you look at the entire system because of the third law. They're equal and opposite. So we can't look at the entire system when we're trying to find these contact forces. We want to isolate either the front mass or the back mass and repeat the process. So let's do that. Let me erase the work that I've got there. And let's look at just the 50 kilogram mass. So mass M1. Now when we repeat the process, we start with our little free body diagram, which we've already got in our picture to the left, but let's do it again. We've got FG1 down, F normal, equal and opposite up. And then once again, I'll put my forces in green that are driving that mass 1. So we've definitely still got direct contact with our 450 Newton force. It's directly touching mass 1, so we have to put it in. It's got some friction opposing the motion. And then also the force that's holding this back is this force FC. So the 100 kilogram mass is pushing back on our 50 kilogram mass with a force we're calling FC. So there's our diagram for mass 1 when we just isolate it. So now we do the same thing. Be consistent as you possibly can. F net is the sum of forces, but now we're only focused on mass 1. So F net is mass 1 times acceleration, ma. And then what are the forces? Well, 450 is pushing it to the right, so it's a positive force. Force of friction is to the left, so it's negative. And this FC is to the left, so it's negative. So there's my basic equation. So if we put in the numbers, I get 50 times 1.04. We know the acceleration of the system, right? 1.04 meters per second squared equals 450 minus. Now remember, force of friction is just mu times the normal. This one here has an equation. And our normal is the same as gravity, m1 times g. So I'm going to replace force of friction with mu mg. So mu was 0.2, my mass was 50, gravity is 9.8, and I still have to subtract FC, so I apologize, I ran out of room there. So when I solve this for FC, and I'll let you guys do the algebra, it ends up looking like this. FC is equal to 450 minus mu mg minus ma, 50 times 1.04. And when you do that, you get a FC of 300 newtons.